Next, we're going to get into how to make measurements here in Chapter 2, and specifically how we do some of the math and how and why we round some of our answers, as well as a powerful tool called dimensional analysis. You hear some people call it stoichiometry. Technically, stoichiometry is a specific chemistry application of it, but it's where you see it the most, but a powerful tool for setting up and doing calculations. And we'll do some calculations that maybe you can do in your head, or maybe you know another way to work it out, and you'll be tempted to do that. But let me encourage you, learn this method for two reasons. Reason number one, it's about the only way I can follow and check your work and give you partial credit if you get an answer wrong. But reason number two is because we will get to a point where we get to complicated calculations that you have no gut instinct for what the answer should be or how to go about solving it. And this tool will help you know for certain that you have set up the problem properly and that you have the ability to get the right answer. As usual, there's a brief application here. I will say that I've had plenty of students ask me why they need to know this, and it is definitely there in the medical field. My mother-in-law was a pharmacy tech for years, and she had to go back and relearn how to do these calculations when she wanted to get a promotion, and she actually came to me and had me tutor her on this exact kind of calculation. And I cannot tell you the number of messages I've received from students who have gone on from my classes and then get a hold of me and are like, that dimensional analysis thing that you taught me is amazing. I knew how to solve the problems. The other people didn't. I was teaching my peers, and I was set up for success because of that. This really is useful, and it's simple too. There's just kind of one little rule you have to follow for doing those calculations, but you'll be surprised how many places this actually comes up, and it can be a lifesaver. Like literally there are times where a doctor puts down a wrong number and a nurse catches the mistake in the calculation there, and it was, wait a second, that seems off, and you have a dose that's too high or too low that can be dangerous for the patient. So it's not to say that every calculation we do has that level of importance by any stretch, but it is an important skill to have. Once again, there's an application question here as well as kind of what our goals are, but I'm just going to dive straight into section 1. So first off, we use what's called the metric system. Properly, it is the International System of Units, but it is abbreviated SI because it is Systems Internationaux, which is a French word. They are kind of the official ones in charge of this. And we have fixed units that we use for all of these. And so, for example, length is meters, volume is liters, or technically speaking, it is really cubic meters. We tend to use liters for fluids, and we tend to use meters cubed for solids. And they are interchangeable to some extent. Mass is in grams. Temperature is in a unit that you're probably not familiar with called Kelvin. There is also the metric system, degrees Celsius, but pretty much anytime we have a temperature in Celsius, we will convert it to Kelvin. And time, which is in seconds. That matches the English system, also known as the imperial system, which honestly I think is the more proper term, because the Brits don't even use the English system anymore. They've gone SI. There are only 3 countries in the world that haven't gone SI, and the United States is one of them. The other ones are like Siam and Sierra Leone or something like that, a tiny country in Asia and a tiny country in Africa. They are the only ones that still use this old, outdated system. Officially here in the United States, the definition of how long a mile is based off of how long a kilometer is. The official definition for a mile is this many kilometers, and it would just make sense to use kilometers. As long as I'm mentioning kilometers, we're going to get into here the prefixes. You've of course heard of centimeters and kilometers and probably millimeters as before. Those are just prefixes that get added onto the base unit of meters. This here's the table that goes through exactly what I just said. It's nicer than my handwriting if you want to take a moment and jot it down, but I'm going to move on. And it's, of course, also in your textbook. Volume is simply the space occupied by a substance. It's how much space it takes up. And volume can be expressed in a cubic distance. Cubic literally means a distance like this, where we have some shape with measurable lengths of edges. Beyond that, we tend to use fluid volumes, and if we have an irregularly shaped object, usually the way that we actually figure out its volume is by doing what's called volume by displacement. We'll get into that here in a moment, and volume by displacement then allows us to measure its volume in milliliters or liters, which we can then convert, if necessary, into cubic meters or cubic centimeters, etc. And for those of you that are in person or hybrid in person, we will be doing labs, of course, where you'll be making measurements with devices. We use graduated cylinders frequently for measuring volumes. Other containers like beakers frequently do have volume measurements on them, but they're not as precise or not as exact, and so then we don't tend to use those. There are some relationships that you should know. For homework, you're going to have to look most of these up when it's time to use them, but for a test or the like, you're going to be given the conversion factors you need, but there are 1,000 milliliters in a liter. A liter is 1.06 quarts, or we could go the reverse process and say that 1 quart is 946 milliliters. One place that's useful to kind of get a good sense of these is actually just to look at your food packages and drink packages. Frequently, they will have both the English and metric units there. What I will say is the metric system is simpler and far superior. You just don't think it is because it's not what you've been taught up to this point. Length is measured in meters, or we can use subdivisions of those, which is centimeters. And of course, when making a measurement, we will use a meter stick or a ruler for making those measurements. And once again, here we have some conversion factors, some relationships of within the metric system, like the meters to centimeters, or we have English to metric conversion factors here. And again, they're nice to be familiar with, but you will be given them when you need them. Mass is kind of strange because it's kind of hard to describe what mass is. Mass is how, to some extent, how heavy something feels, although how heavy it feels is a factor of gravity as well, and a little bit when you hold an object, pressure comes into play as well, how finely pointed it is. And so it's not really a heaviness measurement, it's really a measure of the amount of matter. And as I mentioned in chapter 1, I just call that the amount of stuff in there. The physics definition of mass is that it's a measure of the inertia that an object has, how easy or hard it is to get it moving, kind of. Anyway, the unit is grams that we use. SI does use kilograms technically instead of grams, and there's a reason why. It's a physics reason, but we're not going to deal with large quantities usually, so we're going to tend to measure things in grams or even smaller. And you'll see that on a lot of medications, that they tend to be dosed in milligrams or micrograms. Again, some relationships you should know, again, going both between English and metric. I will say, though, that technically these two aren't true, because these pounds is a weight and not a mass. And on Earth, those two are equivalent because gravity is the same. But if you go into space, you're weightless, but you're not massless. And so something no longer weighs 1 pound in space, but it still has a mass of 54 grams. It turns out there are English units for mass. We're just not familiar with it. It's called a slug. And about the only place where that comes up anymore is the heftiness of some ammunition. Is still measured in slugs. That is technically the English or imperial unit for mass. We just don't tend to use it a lot. And here on Earth, they are equivalent, but not technically. Also, this is one of the few times where our metric unit is bigger. For example, 1 centimeter is smaller than 1 inch. And 1 liter is less than 1 gallon, actually by quite a bit. And it's not really less than, but the spacing on the Celsius temperature scale is bigger than the spacing on the Fahrenheit scale, and the Fahrenheit scale is shifted up by comparison. And so Fahrenheit temperatures tend to be higher than Celsius temperatures, and there are more of them. And this is one of the few times where the metric system or SI system is bigger than the pound. That is, 1 kilogram is bigger than 1 pound. As a side note, I tend to do cursive L's so that we can distinguish them from ones and I's without the serifs. I frequently, when I'm mixing numbers and letters, will take the time to do the serifs, the little tick marks on things like the I and the number 1 there. But a 50 kilogram object is more than 100 pounds. And I find students get this backwards because they get used to thinking that everything is smaller, and then they get it wrong on mass. Your textbook here defines temperature as a measure of how hot or cold something feels. That is okay, and it's what you're used to thinking of temperature as. Technically speaking, cold is a lack of heat, and so when something feels cold, really what you're feeling is a transfer of warmth from your body to the object. When something feels warm, it's the opposite direction. I remember, for example, when the first cousin, the only cousin I had born in my family that was younger than me, it came from one of my aunts. I remember her being pregnant, and she had bought some toys early, and one of the toys she had was this little boat for the bathtub that had a thermometer underneath, so you can measure the bathtub temperature, and yet the kid had a little toy to play with. And I remember looking at that thing and being absolutely shocked that the temperature scale started at 100 and went up to like 120 or higher. And when I had the pleasure of going to Japan, they actually had temperatures on the a valve for the shower itself, and it started at 120 and went up to upper 100s. Like, they like their hot baths. They're used to bathing in hot springs, and I mean, I came out looking like a lobster when I did that, but I had it on the coldest setting, and it was still too hot for me. They ran almost no cold water into their hot water there. But anyway, I remember thinking, going back to my cousin there, that what are we trying to do? Cook the baby? Because it's more than the body temperature. But of course, it turns out your surface body temperature is lower than that 98.6 that you've been told. And it turns out that the 90.8.6 is not really accurate anymore. And we tend to use a range of temperatures, and we don't start to get concerned till just over 100 degrees usually. Or we say that the fever is mild until it gets to just over 100 degrees. And you'll see that in most of the medical literature anymore. And even when you just get a vaccine, your doctor says, watch out for a fever higher than this. It's a sign that you're having a bad reaction. Your internal body temperature is that your surface body temperature is actually colder, sometimes by 10 or more degrees. And so then something feels warm to you only when it's higher than that. And so your bath water only begins to feel warm if it's above your surface body temperature. And so it turns out that the average bath temperature is around 105, 110, of course, same for showers and so on. But that is what you're used to, how hot or cold something feels. However, the actual definition of temperature, and this will come up later on as well, is it's technically the average kinetic energy of an object. That is how fast the particles are vibrating and how fast they're wiggling. And the hotter they are, the more they're wiggling. And it's really a measure of kinetic energy, energy of motion at the submicroscopic level again. At the macroscopic level where we observe, it's how it feels. Anyway, in the metric system, it is measured as degrees Celsius. The SI is Kelvin, and that's what we'll use for most of our calculations. What it is you don't really have such a thing as a negative length or a negative volume. I mean, you can't have something that takes up less than no space. It either takes up space or it doesn't. And temperature was one of the few measurement scales we had where the numbers get negative. It doesn't actually show it over here on the picture, but of course below zero are negative temperatures. And so it turns out that there is an absolute coldest temperature something can be. It's around negative 273 degrees Celsius. It's around negative 460-ish Fahrenheit. And wouldn't it make sense, since there is a coldest temperature, to call that zero? And so that's what the Kelvin scale is. There is a English equivalent called the Rankine scale, and because of that, and it's just a notation thing that we're not going to really worry about, we don't use degrees on Kelvin. Celsius, we use the degree symbol. If you take physics, it turns out there's a difference between Celsius degrees and degrees Celsius, and it has to do with whether we're measuring a temperature or a change in temperature. We just shift where that degree sign is as a notation thing. The Celsius scale is based off of water, whereas the Fahrenheit scale is kind of strange. It was based off of the coldest temperature that Mr. Fahrenheit could get at the time, which was a saltwater mixture. The human body temperature, which he mismeasured and called 100 degrees Celsius, and the boiling point of water, which he thought was 200 on his scale. And he thought that humans being exactly between water boiling and water freezing was an interesting property, which is why he picked those numbers. Why he didn't put humans at 50 and water at 100 doesn't really make sense to me, but whatever. And to be honest, it's kind of nonsensical to think that you couldn't ever get a colder temperature than what he was able to produce, especially because naturally we can get temperatures in nature that are colder than 0 degrees Fahrenheit. And so anyway, that's what he based his scale off of, and it's led to some really weird numbers coming up, like water freezing at 32, and actually when you go for the spacing on the scale should be this, then it causes the human body, the boiling point of water to actually be 212, and it causes the human body temperature to be slightly less than 100, it causes the boiling point of water to be 212. It's just a strange scale, whereas 0 to 100 kind of makes sense and kind of fits with the rest of the metric or SI units. And of course, we're going to measure that with a thermometer. It also turns out that there's just this interesting property where the two scales, Fahrenheit and Celsius, at least agree at the temperature of negative 40 degrees. Only at that time, when you say negative 40, doesn't matter which of those two temperature scales you're using. Time then is measured in seconds. You're familiar with that, and that's seconds for metric, for SI, for the English imperial system. We tend to deal with things that occur fast, and so we're not going to get into minutes and hours, and it turns out that units get weird and wrong, especially because seconds doesn't count up to tens or hundreds, but instead loops around when we get to 60, just like minutes do, and to some extent like angles do. It's just a strange thing, and it goes back to the Babylonians and some other ancient cultures being fascinated and kind of thinking as powerful the number 6, and it's just something that we have preserved through time. But for that, we're going to use a stopwatch, of course, for measuring that. One thing you have to be careful of is, does human reaction speed play a role? There are, of course, electronic stopwatches that are automatically triggered that don't involve humans in there, and those are better. But there's always going to be measurement mistakes when humans are making the measurements, which we'll get into later on. So here, a learning check, just trying to match the measurement to the thing. Rather than using the numbers here, I'm going to just abbreviate these, so length, mass, and volume. And the real way that you identify these is the units here. Of course, on this one here, they tell us it's mass, but the units, kilograms, the grams in there tells us it's a mass. Meters here tells us that it is a length. Grams here again tells us that it's a mass. Liters here tells us that it's a volume. Getting into identifying these, volume is meters cubed, although we can also measure it in liters. For the standard SI unit, mass is grams or kilograms, length is meters, and temperature is Kelvin, although in the metric system it's also degrees Celsius, as I said there, also grams. From here, we're trying to use the SI unit for each of these. It shouldn't have a space in there with the abbreviation, but the SI unit is for height. We're going to have meters. The mass, we're going to have grams or kilograms. SI is going to be kilograms. And for temperature, we're going to have Kelvin here. And again, a metric measurement, but not a technical SI measurement, is degrees Celsius. The others there are all English or imperial units. And that ends section 1.